There you go, I think I have everything set up now. Hi everybody, welcome back to Chem 121. It is the last week of lectures, and what that means is that at the end of this week there will be exam number 2. And after exam number 2, we'll have a review session next week, so we'll have class meeting on one day. I believe I have it scheduled for Tuesday, I'm not sure though, I'll look on the calendar after. And then after that, you take a final, and then you're done. And presumably you will go on to whatever comes after Chem 121, which for chemistry that'd be 131, but I think for bio it's what, 211? Most people who take 121 also take the bio sequence, and so they end up in bio 211 or something like that. I'm not a biologist, so I don't know. All right. What do we got on the agenda this week? So quiz number 8. For chapter 8 is due on Monday. I don't have quiz number 9's due date on there. Let me find that real quick. And then we'll just add it to the bottom so that that information is handy. Because quiz number 9 is due this week. I think it's due Tuesday. And closes Wednesday. Yeah, it does. So let's add that. Because I can do that. So quiz number 8 is due Monday. Quiz number 9 is due Tuesday. My cursor's in the way, I can't see. I can't believe it's March already. And then we have an exam on Friday. So the way that quiz number 9 is going to work is that when it closes on Wednesday, I will then open it up on Thursday so that you can see it. And then we're going to talk about quiz number 10. I guess we'll talk about quiz number 10 right now. After class today, we're not going to finish quiz number 10, but we're not going to finish all the content for chapter 10 today, but I'm going to open quiz number 10 tonight anyway. Quiz number 10 is just bonus points. I don't know what I have it set for. It might even be set to 0 or practice. I don't know. It's different for every class, and I don't have this memorized. I look it up. But the point of quiz number 10 is that you just take it, and it doesn't affect your grade. And then it will be open, just like the previous exam had, like, I want to say it was quiz 5 was open after you took it, but quiz 5 was for credit. This one's not. This is for just practice points, or maybe an extra credit. I don't know why I have it set to. I'll go check. But the intent is that you can take quiz 10 whenever you want to, before or after the final. It doesn't really matter to me. Or take it once before the final, or once before exam 2, and then once after, if you'd like. But the results will be posted immediately. Your score should pop up in the gradebook immediately. It should all just be automatically set to, like, up here. And then you can review what you did on those exams, because then you won't go into the exam blind and not knowing, like, oh, what was the chapter 10 content? Will there be a study guide for exam 2? There should be. Is it not revealed yet? It might be invisible. Let me double check to see if... Let's see here. Yeah, it's invisible. That's a problem. Okay. So let me make that visible real quick. All these things that I think that I do. But there are like 60 billion moving parts to Canvas. Let me see here. Where is... So there's Study Guide 2. Publish. And then I need to do that for this other class. Unpublished. Why did that unpublish? Oh, because I didn't hit a different button. There we go. Okay. That should be visible now for everybody. And if it's not, let me know. Because that is Canvas being stupid. So, it should definitely be there now. But yeah, there is a study guide for exam 2. And it covers chapter 6 through 10. Okay, so last week, where we left off, we were talking about acids and bases. So I did the very basic introduction, about what an acid is, some various properties, and then what a base is, various properties. We didn't really formally define them chemically, and so our task today is going to be to define them from a chemical perspective, like what specifically goes in an acid and a base. And then we're going to do some problems related to that so that we can predict how acids will behave in given situations. Because acid-base chemistry is very important. It turns out that acids and bases are extremely common physiologically. For example, acids are in your belly. You have stomach acid, which breaks down food. And understanding how the digestion process happens is pretty important to understanding how we can explore cell metabolism and things like that. Like, why do we need nutrients? Here's why. And acids and bases are the start of that. So, all right. We're going to define acids and bases in 2 different ways. This first one is kind of garbo because it's not that it's bad, it's just incomplete. And then the second way is going to be much more rigorous definition. And then the third one will not discuss it at all because it's just beyond the scope of this class. But it is just as effective as the second one. So, and those are listed on the screen here. Arrhenius is the incomplete one. Bronsted-Lowry is the one that we're going to use for the most part. And then we're not going to talk about the Lewis definition of acids and bases yet. So we're going to define acids and bases by the following in the Arrhenius method. And, oops, I don't know why that disappeared. Come back. An Arrhenius acid is any substance that dissociates. In other words, it splits into ions. And one of those ions is H+. An Arrhenius base is the same sort of situation. Splits into 2 pieces. But one of those pieces is OH-. So acids are H+, and bases are OH-. Remember that OH- is called hydroxide. Hydroxide is the main component in basic solution, whereas H+ is the main component in acidic solution. Now, H+ is literally just a hydrogen nucleus. Well, hydrogen only has 1 proton in its nucleus, and that's it. So H+ is actually just a proton flying around by itself. I know what happened there. I'm sorry. I think I hit the space bar trying to move the slides, and if I do that, you couldn't hear anything I said. Yeah, it muted itself. I'm so sorry. Let's go back here. I don't know where I, probably here. So we talked about acids and bases. Sorry, thank you. Yeah, no, because I'm clicking back and forth between this window and then also the, what I'm using to stream. If I have clicked on here and then I hit the spacebar, everything mutes. So, I'm glad that you noticed that. So we'll go back and talk about this again. Okay, so H plus is just a proton, and what that means, excuse me, what that means is that it is very, 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 very tiny. A hydrogen ion is just the nucleus, whereas a regular atom would have its electron cloud. And the electron cloud is way bigger than the nucleus itself. So we end up with this really teeny tiny charged thing. And what that means is that water, which is polar, water gets attracted to this extremely quickly. And so if H plus pops off from any acid dissociation, it will immediately just bonk into the first water it sees and form this H3O plus thing. And we call that hydronium. Hydronium is just water with an extra H plus on it. And so we retain the extra H and a plus. And then I was drawing its Lewis structure. And that looks like this. And there you go. So we're not going to say that just H plus exists in water by itself. We're going to assume that H plus always finds water. In reality, it's a little bit unclear what happens. It's not well understood, I guess is what I will say. Like, it's anticipated that H3O plus is what we form, but we might actually form like some little like conglomeration of a bunch of waters around a proton or something like that. For our purposes, we're just going to call it H3O plus, but because both terms are understood to mean the same thing, depending on the textbook that you have, you may see H plus or H3O plus. They are intended to be the same thing. And the important thing is, it is a positively charged extra hydrogen which behaves as an acid. Now, the act of acid-base chemistry is going to be us passing around the H plus all over the place. You might have noticed that with hydroxide OH-, that's a really easy target to pass an H plus to, because H plus and OH- would make water, right? And so that's going to be the premise of these types of reactions, is if I can take this thing and react it with H plus, together, these would make H2O. And so that's where acid-base chemistry is going to come in. Oh, I have it written down here, so there you go. So in the same way that acids dissociate to make H plus and something else, bases also dissociate to make OH- and something else. And the part that we care about are the H plus and the hydroxide. All right. So this is called, this process down here at the bottom here. Oops, didn't click. This is called an acid-base neutralization. Now, it turns out that H plus is our acid. We're going to focus on that. H plus slash H3O plus. They're the same thing. But hydroxide is not the only base. Turns out that OH- is not necessarily the only thing that can react with H plus. There are other things out there too. For example, ammonia turns litmus paper blue. How on earth does this happen? And so what we have to do is we actually have to change our description here from just, oh, it makes H plus or OH- to something different. And so this is where the Bronsted-Lowry definition comes in. It is more specific. While the Arrhenius definition is helpful because you can say, oh, it's got OH minus in it, it must be a base. And that'll be true. It's not complete because the Bronsted-Lowry definition will include things like ammonia or other basic substances like the base pairs in DNA or caffeine or nicotine or stuff like that. And so here's our new definitions. And these are going to be the definitions that we should focus on for our understanding of acids and bases. The first definition doesn't really look that different, and it's really not. A Bronsted-Lowry acid is any substance that, when you split it apart into pieces, one of those pieces is H+, and you can say that the H+ is donated to the solution. Now, the Bronsted-Lowry base, on the other hand, is very different in definition. A Bronsted-Lowry base may or may not dissociate, but what it does do is it reacts with the H+, and the total amount of H+ in the solution is reduced. So, we'll just highlight the whole thing. Acids add H+ to solution, bases remove H+ from the solution. So therefore, anything that reacts with H+ would lower the amount of H+ in solution because it's reacted with it, and thus would be a base. And amongst these would be things like ammonia, which I don't know if I have it written on here. So there we go, that's what I want. Now, how do we get these two equations? Let's go over here and look at this in more detail. That's not quite right. Okay. Let's look at this reaction first. So this is pretty straightforward. So if I have HCl and it reacts with H2O, the first step is going to be my dissociation. And when my acid dissociates, I get two pieces. Then the next step is going to be that this reacts with water. And then the result is whatever is left over. So H plus and H2O would make H3O plus. And then we've got this left over, and we'll just write it right here. Now, those are oppositely charged. Should they form an ionic compound? It turns out that in water, they don't. They're completely soluble. Just like sodium chloride is soluble, H3O plus and Cl minus are soluble. For our purposes, that's good enough. In reality, the bond between H and Cl is very, very weak relative to the new bonds that we formed by hydrating the solution. Or by hydrating the acid, I should say. All right, so there's our acid dissociation. That one's pretty straightforward. Let me get the other one set up here. Okay, this one's a little more complicated. So we'll scroll this down. How the heck does this happen? So the first step is if for something is going to be a base, then it needs to react with something that is behaving like the acid. And it turns out in this case, water is going to do that. In this case, water is going to be the one that dissociates. Can water do this? Yeah, absolutely. However, it's not as common as you'd think. And we'll talk about this in a little bit. And you might notice that, like, well, wait a second, if I'm making an acid and a base, well, yeah, they neutralize, which is why water is neutral, right? Now what's going to happen is that these two are going to react with each other. And that makes me this, and we got this guy left over. So when ammonia is put into water, we still make hydroxide, and so therefore the solution is basic, and we would say that ammonia is a base. But we do so in a very indirect fashion. And so that's why it's confusing to use the Arrhenius definition for things like ammonia, because yeah, ammonia does make hydroxide, but it steals the H plus off of water to do it. The Arrhenius definition, therefore, requires a lot more steps of logical thinking and understanding what's going on. The Bronsted-Lowry definition, however, just says, oh, okay, it reacts with H+, therefore it must be a base, because I'm removing H+ from the solution. And that's easier to understand conceptually. You don't have to do as many steps here. All right. So any questions, let me know. But the next step of what we're going to do is we're going to look at all reactions kind of like we just did with this one. So at the bottom here, I wrote down in purple that one thing behaved as a base and the other thing behaved as an acid. We're going to start doing that with any combination of things, and we're going to try and identify what's the acid and what's the base, and that will allow us to predict something about the result of the reaction. So I'm going to give you this, and I'm going to highlight the reactants here. And what I want you to do is tell me, for the reaction shown, which reactant is behaving like an acid and which reactant is behaving like a base. Remember, we're using the Bronsted-Lowry definition, so don't go hunting for H pluses or OH minuses necessarily. Tell me which one gives up the H plus to make it increase the amount in solution, and then which one accepts it and reduces the amount in the solution. So one of those is an acid, one of those is a base. Type it in the chat which you think is which. All right, I'll give you 30 more seconds to puzzle it out. My hint to you is look at what the products are and see if that helps you determine where the H plus moved to. All right, let's go over the result here. If I can find my pen. There it is. All right, so in order for this to happen, I need to make H3O+, which means that I need to get an H onto here somehow, right? And so the way that this will happen is I will split this into two pieces. One of those is H, and the other one would be Br. H plus and Br minus. So this would be my dissociation. And then the Br just kind of hangs out, and that's what we get. So our labels would be HBr is our acid, and water is behaving as a base. Very good. All right, let's do another one. How about for this one? We've already done this, but now I want you to think about the pieces with from your notes and what you've seen so far. On the left side, oh, I should highlight them, sorry. Let me do that real quick. On the left side over here, which of these is the acid, and which one is the base? And my hint for this one, as in addition to looking and seeing and predicting what the result is based on what you've started with, my other hint would be don't get pigeonholed into thinking something is always something. Okay, look at what evidence you have based on the products of the reaction. Okay, I'll give you a minute to puzzle this one out, and we'll go over the result in just a second. All right, any ideas before we take a shot at the answer here? All right, let's see how you did. All right, so in this case, we have to split H2O. So here's my dissociation. And then NH3 is going to react with it to make NH4, and then we have our OH left over. Okay. Who added H plus to the solution? That was water, because, oops, I wrote the wrong thing. I was going to say the word because, and I was going to write the word because and not base for some reason. That was silly of me. So water is our acid because it increased the amount of H plus in the solution. Ammonia is the base because it reduced that amount of H plus. It consumed it. It used it up. All right. So we've got the left side of the equation. Now you might notice that this reaction has a double arrow here. So I'm going to clear all this out. And now what I want you to do is I want you to do the same thing, but for the reverse reaction, which I'm going to highlight in a different color here. There we go. Okay, so now I want you to do the reverse reaction. When these two things react with each other, and to turn back into the reactants, which of those on the right side is the acid, and which of those on the right side is the base? I'll give you a minute to think about that too. All right, one more minute. We'll go over the answer. All right. Where did my pen go? There it is. Okay. So first, we need something to dissociate and provide an H+. And I cannot get it to select the color. I don't know why my tablet does this sometimes. There we go. And so this must be the thing that does that. So there's our dissociation. And then this would react with this thing. And that would get us our H2O back. And then we have the ammonia left over. So the thing that dissociated was the acid. And the thing that reacted was the base. There you go. So we have now created a reversible acid-base reaction and shown which one's the acid in each case and which one's the base. All right. Now, water in this case was kind of interesting because here water was acting like an acid. In the previous example over here, water was acting as a base. Water can do either thing. And we're going to come back to that in a little bit. We're going to give it a proper term for things that can react in either capacity. They can either accept an H+, or they can get rid of an H+. So some substances do behave like both. All right. Now, for our reaction that was reversible here, when you have a base react with H+, it becomes a conjugate acid. And what that means is that if we go back to this reaction right here, and we label what everything was, and what it becomes, you'll notice that ammonia started as a base and then became NH4+, or ammonium, which is an acid. And if it gets rid of its H+, it becomes a base again, and it goes back and forth like this. When you do these reactions, you're going to notice that this always happens. And so what these are called conjugate pairs. Likewise, we'll get a different color here. These two right here are also conjugate pairs. Conjugate pairs always differ by an extra H+ on one or the other. Not both, obviously. They'd be the same if that was the case. But the difference between two members of a conjugate pair is always H+. Either it is gained or it is removed. So our task in a reaction is going to be not only to identify which ones are the acids and the base, but to also link the conjugate pairs together. So we're going to do that. So in this reaction, here's our base that we said before. This is the same one as on the previous slide, actually, I realize. And it is linked to a conjugate acid because they differ by just H+. All right. In this example, we're just doing the same thing here. So here I have water, which was my acid. It gave away H+. It is linked to OH. It is the conjugate base of water. Now, it's important to note that conjugate acids and bases are conjugated for only the reaction that is shown. So this is not something where I would ask you, like, what's the conjugate base of water? Because you would not really be able to answer that without the context of the reaction. So don't commit acids and bases to memory with the intent of trying to figure out what the conjugates are. Look at the context of a reaction, and that will give you the information that you need to solve the question. All right. Here's another reaction, and what I want you to do is to do what we've just described. On the left side, on my reactant side, one of those is an acid and one of those is a base. On the right side, the products, the reverse reaction, one of those is an acid and one of those is also a base. And then I want you to link the conjugate pairs together. So first identify which one's the acid, which one's the base on each side, and then link the pairs together. I'm going to give you 2 or 3 minutes to try and do that, and then we'll go over the answer. All right, 1 more minute, we'll go over the answer. All right, let's look at this in a little more detail. So in order for this to become this, it looks like it's losing an H+, right? Because there's one fewer hydrogen and the charge got dropped down to -1. So my dissociation will be here. So I'll have H2PO4- and H+. So there's the dissociation. That must mean that since this dissociated, it must react with this one. And there's my reaction. So, since H3PO4 donated the H+, it's the acid. Since water reacted with it and then removed it from the solution, water's the base. Okay, let's look from the other perspective now. I have to pass the H+ back over to the other thing. So this must be the one giving it up, so I can get the water back that I had before. So there's my dissociation. And then my reaction would be with this. So that makes this the acid and this the base. So now we have figured out which one's the acid and which one's the base on both sides. And then the next thing that we need to do is we need to clear all this. And then we got to link the conjugate pairs together. So we would link this with the other thing that differs by H+. So there's my conjugate pair. And then this would link with the other thing. So there are my conjugate pairs. Remember that in each conjugate pair, you must have one is an acid and one is a base. And on each side of the equation, one is an acid and one is a base. Because acids react with bases, and after an acid reacts, it becomes a conjugate base, and vice versa. All right. So there you go. There's our answer, and that's exactly what we wrote down. All right. Got another one for you. Try this one. Tell me who's the acid and who's the base on both sides of the equation, then link the conjugate pairs together. I'll give you 2 more minutes to try it. All right, let's go over the answer here. Now, I'm going to look at the water and notice that it's going to turn into hydroxide. So that means that I'm going to need to split this into these pieces. So there's my dissociation. And then the H+ is going to react with the other thing. So that means that water here was my acid, and bicarbonate was the base. Going in the other direction, I have to have one of these two pieces dissociated to H+. Now I'm going to do the wrong thing here and show you how you recognize it's the wrong thing. If I split this into H+, what's the other thing that I have? Well, it would have been this, right? Do I see this over here? Well, it's not, right? So this is not what's happening in this reaction. Could this happen? Potentially. But is it happening here? No, it's not. So that must mean the other thing is what we want to dissociate. So we'll split this up into H+ and bicarbonate. And hey, this one does show up right there, so this is correct. And then the H+ will react with the other thing. So therefore, this produced the H+, this is my acid. This accepted it, this must be my base. And then finally, we'll just clear all this. Let's link the conjugate pairs together. That's the highlighter, not the pen. So my H2O will link with hydroxide, and the bicarbonate will link with the carbonic acid. And so there are my conjugate pairs. And lo and behold, that's exactly what we just wrote. All right, I've got a few more of these for you to try. Now, just because a compound looks weird doesn't mean you can't follow the same process. So don't be afraid that you just see this pyridine all of a sudden down at the bottom here, the C5H5N. It looks really strange, like what the heck is that? But based on the information that you can see, you should be able to predict which one's the acid and which one's the base. Okay, so go ahead and try these two problems. I'll give you 5 minutes to do it. Then we'll go over the answers, and then we'll take our break, because we're due for one. Okay, see you in just a little bit. Oh, where'd my cursor go? There it is. one more minute, we'll go over the answers here. All right, let's go over the answer here. We'll put this on the screen. That's not the one I want. There we go. We're going to do this just like we did the others. So I do have to write the whole thing down again. You'll notice that I'm kind of ignoring the phases because who cares, right? All right, so I need to have one of these dissociate to produce the H+. And the way that we're going to do that is, well, I have H2O and it becomes H3O+. So if this dissociates, I'd end up with OH-. That's the opposite of what I want, right? So that's not what we're going to do. Let's get rid of that. But if I do this, then I get the pieces that show up in our reaction, right? So there's my dissociation, and then this would react with this. So therefore, this must be my acid because it dissociated into H+. And this must be my base because it reacts with the H+ to remove it from the solution. Okay, let's do the same thing. This has no H+ to dissociate, right? So it can't possibly be the acid. So that leaves this. So that means this is my acid. It did the dissociation. This must react with that, which makes it the base. And then, let me just loop through all of that. There we go. Boop. Oh, that's not what I meant to do. There we go. So now we can link the conjugate pairs together. So I've got my acid, and it must link to the other thing that has sulfur in it, which is the base. So there's my conjugate pair. They differ by an H+. The other two must also be a conjugate pair. They differ by H+ as well. All right, and then the second one down here, so we've got water plus pyridine makes pyridinium. You'll notice that the H's don't combine here. That's because this H is an acid. Goes in the front. And we got hydroxide. All right, which one dissociates? Well, it's got to be this water, right? Because I got to make an OH- later. So that means this is my acid. This then reacts with this, which is the base. And then over here, I need to turn the OH into H2O plus, or H2O again. So that means that I have H+ and pyridine. So that dissociated, so this is my acid. This will react with this one, which is the base. Oops, I kind of chopped part of the 5 out there because I don't care. It doesn't matter. So I'll link H2O with hydroxide. There's my conjugate. I'll link pyridine with pyridinium. There's my conjugate too. All right, that's conjugate acids and bases. So your task for this section is to be able to understand what acids and bases are and determine how they react by looking at conjugates in these types of reactions. If you have any questions, let me know. All right, we're due for a break. I'm going to put this on the screen. And I'll see you in about 10 minutes. So catch you in a bit. Alright, we are back. We'll get our creepy almost finals week music out of here. Alright, so the next thing that we're going to talk about is strong and weak acids and bases, but we have a few other things to cover before we do that. The first one we're going to use is the term for substances that can be either an acid or a base. So that's an either, not a both. So something is never an acid and a base at the same time. It depends on the circumstance. And so particularly important here is water. Water is the substance we've run into that does that. There are others, but water is the key one here. So on the screen, I have a case where water acts like a base because the H plus comes off of nitric acid here and goes onto it. But in this case, the H plus comes off of water and goes onto the ammonium. So here water is acting as a base. Here water is acting as an acid. Because it can do both, we're going to give it a term. So the term is called amphiprotic. Something is amphiprotic if... Sorry, I thought I heard my cat scream. That was weird. Something is amphiprotic if, in one circumstance, it can be an acid, in one circumstance, it can be a base. Now, it has to be that particular substance. So, for instance, if I was looking at HNO3 and then later I was looking at NO3, these are not the same thing. So, HNO3 is not amphiprotic in this, as shown here. Only water is doing this, because these are two separate reactions. And then lastly, some other terminology that we have is labels to describe how many H pluses are potentially able to pop off of something. So for example, hydrochloric acid and nitric acid both only have one H plus to give away, so they are examples of what we'd call monoprotic acids, so mono being one. And then we have diprotic and triprotic. And there are some examples of those too. So carbonic acid and sulfuric acid are both diprotic acids. The only triprotic acid I could think of was phosphoric acid. I'm sure others exist, but that was the one I thought of. And there are more protic acids out there, so there could be a tetraprotic, etc. I'm guessing that if something can be a base or acid, it will be one of them based off of what it is being combined with. That is correct. Yeah. It absolutely depends on what you're reacting it with. And it will always work in that same direction for the given substance. So if I go back here, in the reaction of water and ammonia, so the second one down here, ammonia is never going to be the acid. So ammonia will not give up its H plus to H2O and then create NH2 minus. That's not a thing that will happen. It always works in one particular direction for a given substance. All right. Last thing for diprotic and triprotic acids is if they dissociate multiple times, they do so in a stepwise fashion. So I do not give up both of these at once. I give up one first. So there's the other one. And then I give up the other one. So this is two reactions, a stepwise reaction. And you'll notice here that in this case, if I'm going backwards, HSO4 minus would be a base, but in this case it's giving up its H plus and it's an acid. So HSO4 minus in this case is another example of an amphiprotic species. It can go in either direction, depending on what it's reacting with. If it reacts with water, it'll give it up, but if it reacts with hydronium, it will accept it. It being the H plus. All right, let's move on to describing the strengths of acids and bases. This section is going to be important to us because it's going to answer a question. When do we use the reversible arrow, and when do we use only the forward arrow? It has to do with the strength of the acid and the base, like we talked about in the equilibrium section. We're going to define a strong acid as something that dissociates completely and does not recombine. And that's going to be something like this for HCl. Now, I have written the equilibrium arrow to match with your textbook, but honestly, this is really stupid and no other textbook does this. The correct way to do this is, instead of having a shorter arrow for the reverse direction, the correct thing to do is to just draw a forward arrow, and that's it. So you may see either of those, but what I'm going to try and do is I'm going to try and just draw the forward arrow to represent an irreversible reaction, because the substance was, say, a strong acid. So in this case, what happens is that HCl dissociates, but the reverse reaction doesn't happen, so H plus ends up on here, and I get these, and then it's done. In my solution, I would only find H3O plus and Cl minus as my active species. I would not find any HCl. And then water's just always everywhere anyway, so. So, if your acid is a strong acid, we only use the single arrow, which I just erased, unfortunately. Alright. Now, it says down at the bottom it is an equilibrium and the reverse reaction can occur. That is very technically true. For our purposes, you can just ignore this. Essentially, only the forward reaction occurs. And for our purposes, that's good enough for this class. All right. What are the strong acids? These are the 7 strong acids: HCl, HBr, HI, high, HNO3, HClO3, HClO4, and H2SO4. Now, specifically, H2SO4 is a strong acid for the first dissociation only. So, this is not a strong acid. So, don't include HSO4 minus in there. If you're not one of these 7 acids that's shown on the screen, then you are a weak acid. A weak acid means that it only dissociates a little bit in water, and so the equilibrium looks like this, according to your textbook. But in reality, this arrow is stupid. And so what we use to indicate this is that both arrows go in both directions. So the reverse reaction is possible, and in fact is much more favorable than the forward reaction, which is why in the equilibrium chapter where I showed you acetic acid, which is also a weak acid, that there was 99.5% of it in solution and only 0.5% of it had dissociated. So weak acids have the double arrow. Strong acids have the forward single arrow for our purposes. Now, the same thing that is true with acids is true for bases. There are strong bases and weak bases. For bases, there are only these strong bases, and they are all hydroxides, and they are specifically paired with these metals. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium, strontium, and barium hydroxides. These are all the strong bases. Any other base is a weak base. And therefore, you would use the double arrow. So if I wanted to write the equilibrium between ammonia and water, I would do this. And instead of this stupid small arrow, I would write a double arrow. So there you go. That's strong and weak acids and bases. really what this comes down to is you just have to know which ones are strong and which ones are weak. That's going to require you to write them in your notebook and then just have them in a little table handy. And then when you go to take the exam or the final, reference that table and have it just available for you. All right, and there's our summary. Now, regarding conjugates of acids and bases, if the acids are weak, then all the conjugate, or if the acids and bases involved are weak, then all the conjugate acid-base rules that we discussed apply. Now, if you have a strong acid, for example, let's go over to do this thing. And we'll put what I'm talking about on the screen here. Where'd my cursor go? Oh, there it is. I'm holding the pen in the wrong hand here. I want this top part here. Let's talk about what this point means real quick. We'll just scroll this down. So I'm going to take a strong acid, and I'm going to react it. And so if we were to label these, we would say, okay, this is the acid, and this is the base, because this dissociates, and then the other thing reacts with it. But on the other side, if I wanted to combine these two together, I could say that Cl minus could react with the H plus over here to make HCl, but you'll notice that there's no reverse arrow, right? And so instead of it being a conjugate base, we call it the conjugate. So here's my conjugate right here, but its strength is effectively neutral. Cl minus is neutral. It is not a base. If you put it into water, it will not create HCl. So if you have a conjugate of a strong acid or base, the conjugate will be neutral. All right. There's the homework practice for this section too. So that's just a terminology check. So make sure that when you are doing a later section that we're going to talk about, which we'll do tomorrow, the buffers section, make sure you understand what a strong acid and what a weak acid is versus a strong base and a weak base, and have that table handy with all the strong acids and all the weak, or the strong bases available, because it will be very relevant when we talk about buffers. But for now, really, it's just going to be a definition. All right, I think the last thing that we're going to be able to get to today is this section here, so salts and neutralizations. We'll probably do pH tomorrow. And then we'll talk about the last lab, because the last lab is involves pH, I believe. Or is it solubility? I'm going to have to look it up. I forget what the last lab is. I've changed it once or twice, so. But we'll talk about the lab tomorrow. All right, what is a salt? Salt is the thing that you go into your spice cabinet or cupboard and you sprinkle it on your food to make it taste good, right? Now, normally I would be like, haha, no, that's silly. But in reality, that actually is where the term comes from. Table salt is a salt. It's the most common salt, though. Table salt is what we sprinkle on food because it's delicious. And the reason that we use NaCl versus any other salt is, well, if you've had to use salt substitute like KCl or whatever, it tastes metallic and awful. And people who have too much sodium in their diet and need to take that for blood pressure reasons or whatever, hate it. And I've tried it, and it's just tastes very metallic, and it's not great. This is the most tasty salt. That's why we use that. But where does the word salt come from? Specifically, a salt is an ionic compound that is the result of an acid-base neutralization. When an acid and a base react with each other, you get two products. One is salt and the other is water. Now, specifically, the base has to be an OH-containing base. If the base doesn't contain OH, you cannot make water. You still get a salt, but you don't get water as a result. Alright, with that in mind, now that we know that acid plus base, if the base has hydroxide in it, equals water plus salt, we can use that to figure out what products are. So when we look at an acid-base reaction, what we're going to try and do is we're going to try and find water. And there it is. Wow, my pen is just not cooperating with me today. Sorry. Let's try this again. Water. There we go. So there's my water. Everything else must be the salt. And you can see that right here. So that's going to be our goal. We're going to look at reactions, and we're going to find all the waters that we can to completely neutralize all the acids or bases. Everything else that's left over must be the salt. Oops. And again, this is an acid-base neutralization. So just in case you didn't catch that when I said before. So let's do a few of these. Let's look at some of these. Let's do this from scratch here. So I want to write the reaction for the neutralization of sulfuric acid and potassium hydroxide. So let me pull that up on the screen here. All right, and so I know I'm going to make two things. One's going to be water, and the other is the salt. So when you're given these types of equations, the acid-base neutralizations, write it out like this. Write your reactants, draw the arrow, and then put water plus salt. All right, so now we got to find water. First, we got to dissociate everything. So I'm going to split this into H+, SO4-. Now, I know that this would go in two steps, but I'm going to just do one and then the other because I want to just keep the reaction a little bit simpler. So I'm going to completely dissociate everything. I'm going to do the same thing over here. All right. And our goal is to find water. So if I do this, I found water. There it is. Now, did I completely neutralize all the acid or the base? Well, no, I still have some over here, right? So in order to do that, I'm going to need another K plus and another hydroxide, right? So I need to do this. And now I can completely neutralize my acid and get another water out of it. That's my foot kicking the table, sorry. You could probably hear that. I'm just like tapping my foot against it and then my foot falls off it, I guess. I don't know. Now the last thing that we have to do is everything else is the salt. So let's get another color here. We'll do red. This is my salt. What salt do I make? Well, I make two K pluses and an SO4 2-, so this is my salt. Just like we did when we were making ionic compounds all the way back in Chapter 4, right? And so there's the reaction for the neutralization of sulfuric acid with potassium hydroxide. So again, to summarize what we did, not FID, find all the water and neutralize. And then everything left over is the salt. Okay? So that's how we do acid-base neutralizations. Make sure to balance the equation as you do this, because you want to make sure that you have a balanced chemical equation for any equation that you write. All right. So you've seen my demonstration. Now I want you to try it. So let's go through this here. So do. There you go. So that's exactly what we just did, right? All right. Here's another one. Actually, I'll just put them all on the screen here. So I'm going to give you these three. Oh, I guess we are going to get to pH today, huh? Okay. I'm going to give you these three reactions. I'm going to give you like 6 or 7 minutes to do these. Once you get a reaction, type it in the chat here. So I'll number them for you. So we'll say 1, 2, 3. Go ahead and solve those acid-base neutralizations and write out the product once you get it in the chat. All right, I'll see you in a bit. Let's do 2 more minutes, and we'll go over the answers here. All right, let's go over the answers on this screen. I gotta click on... Oh, you know what? We'll leave that on the screen here. We'll just scroll up like this. I keep misplacing the pen. There we go. All right, so for the first one, we got KOH and HPR. So let's split this into its ions. And we'll split this into its ions. And then we've got water plus salt. Okay, well, I found water. Here it is. And I neutralized everything. So the remainder must be my salt. There you go. There's the reaction. All right, for the second one here, this is just like what we did before. What do we got? Rubidium hydroxide. So we'll split everything into its pieces. So what ions does it form? Rubidium ion and hydroxide ion. And then we'll do that with my sulfuric acid here. Tear off all the H pluses. And then we'll find water. So here's a water. But I have leftover H plus, so I'm going to need to... Oops, I gotta do this. I clicked the wrong thing. There we go. So I need a second one of these to neutralize the other H plus from the sulfuric acid. So there's my 2 waters. And then everything else that's left over must be my salt, right? And there you have it. All right, the last one is complicated only because you have to keep dissociating things, but it follows the exact same process here. So we got phosphoric acid, and we've got calcium hydroxide. So again, we're going to make water and a salt. Let's split this into all its possible pieces. And then we'll do the same thing over here. So we got a calcium, and then I've got 2 hydroxides. Really, knowing all those charges, that's the thing from Chapter 4. We're going to have to know that. So make sure you immediately can look at that and go, oh, calcium is +2. Phosphate is -3. It's a polyatomic ion. All right, let's neutralize everything that we can. So we're going to neutralize these 2. And we're going to neutralize these two. I'm not going to draw the connector across, just because it'll get in the way here. But I need more hydroxides to neutralize this last H plus here, don't I? So I'm going to do this. We're going to add in another calcium, and another 2 hydroxides come with it. And so that allows me to neutralize these, but now I have extra hydroxide, and so I need to add another phosphoric acid here, and so we'll do that. That lets us neutralize these two, but again, I need to neutralize more acid, so I gotta go and erase this guy. And I gotta put a 3 there. And this is the process that we just have to keep doing until we neutralize everything. Fortunately, this is the last time we have to add something because these and these now neutralize. So I have neutralized all the water and I made 6 of them. Lots of water. Everything else that's left must be the salt. And that would be calcium with a 3 there, phosphate with a 2. Calcium phosphate. All right, there you go. I'll tab back to the previous lecture slide so you can get the homework practice there. I'm going to introduce pH to you, but we're not going to do the calculations today. We'll do calculations with pH tomorrow. So make sure you have your calculator. We're going to use, on the very last lecture, a new button on your calculator marked log. It'll be great. I kind of hate that that's at the end of the quarter, but that's just sort of how everything works out. All right. The pH scale is entirely used for our purposes to determine numerically if something is acidic or basic or neutral, and we assign a number for these extremes or the center point, which is where neutral is. The range of numbers is usually between 0 to 14, but this is not a hard limit. You can go below 0 and have a negative pH, which means super, super acidic. You can go above 14 and have a pH that's higher, which means super, super basic. It's just very hard to do so because of how the math works. And we'll talk a little bit about that tomorrow. But for now, what you need to know is that the numbers that are lower, like smaller, are going to be acids. So lower numbers are acidic, higher numbers are basic, and then the midpoint is 7. 7 is our neutral point. If you are below 7, you're an acid. If you are above 7, you're a base. If you are 7, you're neutral. And because we have ascribed these names to them, acid, base, or neutral, they have the appropriate things that come along with that. So something that's acidic will have lots of H plus in it. Something that's basic will have all of the H plus absorbed. In other words, there will be lots of hydroxides. Now, I believe I have a colorful scale on this page here. There's one typo on this page, so this is not supposed to be a 0 in here. This should be a 1. But other than that, this slide, this is the last slide we're going to do. This slide tells us how much H plus is in the solution relative to something that is pH 7. And you'll see why the numbers work out to be kind of weird. We're going to zoom this in real quick. All right. So the number on the left is going to be our multiplier from pH 7. So if you are pH 6, you have this many more times acid than something that's pH 7. So H plus, there's going to be some amount of H plus in a neutral solution. But a pH 6 solution has 10 times that amount. pH 5 has 100 times that amount. pH 4 is 1,000. It's all factors of 10, you'll notice. And this is where the log scale comes in. Log is just a bunch of powers of 10 condensed. So when you take log of this number, what it spits out is going to be the pH. Now, there's a little bit more nuance than that. We're going to type in a different number, but it's going to be based off of these numbers here. Oops, sorry, I meant to just have the hand sweep around here. So each time you step down to the next pH, you are increasing how much H plus is by a factor of 10. And on the right, we have a list of things that fit into these categories. Water is our midpoint. Water is pH neutral. We define water being pure, as in there's nothing else in it. It's just water, no ions of any sort. So not tap water, but pure water with absolutely no CO2 or anything dissolved in it. That's pH 7. You'll notice that biologically, going down the pH chart or going up, things start out safe and then they become more and more caustic to the point that they get dangerous. So urine and milk are safe. Urine has to be safe. Like, you wouldn't drink it, obviously, but it's not dangerous while it's in you. It doesn't like corrode away your bladder or your urethra or whatever. Like, it's not hazardous in that regard. So its pH must be relatively close to water. Milk is the same way. For the same reason, it's stored within an organism, right? So it's stored within like a cow or within the breast or whatever, and so it must have a pH that is not harmful to the body. Coffee is something that we consume regularly, so it cannot be that dangerous, right? And it turns out that coffee is slightly acidic, but not terribly so. It's pH 5. Acid rain we're going to talk about tomorrow, because acid rain arises from a specific reaction in the environment. And that's particularly interesting to an inorganic chemist like me. So I'll talk about that in a few slides tomorrow. We'll come back to that. But other things that are acidic are things that we said at the start of the acid-base chapter on Wednesday last week, where we said they were tart and they had this like sourness to them. So those are things like tomato juice, grapefruit juice, lemon juice, etc. Now, eventually you start to get past things that are safe for human consumption. For example, stomach acid is not safe for human consumption. It stays in your stomach and your stomach is protected from acids by a layer of mucus. But if you vomit, then the hydrochloric acid burns your esophagus and your mouth and can also corrode your teeth. And cause them to dissolve, so that's not fun. And then 10 times stronger from stomach acid is battery acid, which do not consume. Like, don't even look at or touch, right? Because you can see that the amount of acid relative to water gets real concentrated very quickly. 10 million times more acidic than water is pH 0. We can go the other direction. And when we do this, we get 10 times less acidic. So there is some amount of H plus in water. If we have 10 times less H plus, we get pHs that are higher. We lead up to the base side, because remember, a base has very little H plus in it. We've absorbed it all. And so those are things like pure water, baking soda, toothpaste, milk and magnesia, which is what you use when you have an upset stomach. It's really powerful. And then past that, it starts to get dangerous. Like, you don't drink ammonia. You shouldn't drink or consume soap or bleach or oven cleaner or Drano. Like, these are very dangerous things for the purposes of, like, exposure. If you, like, get oven cleaner on your hands, like say you took the gloves off and then you touched, like, part of the oven, your skin immediately becomes very, like, slippery. That's because it's dissolving your flesh. Like we said with soap. Soap is usually pretty basic. The point of soap is to safely dissolve your upper layer of flesh so you can clean yourself, because you don't want those skin cells anyway. They're dead. Okay? So that's the pH scale. Just from a glance. We're going to be working with numbers that will fall on this scale. And so tomorrow when we start calculating pH, like, we'll calculate the pH of water and we'll get 7. And then we'll calculate a pH of an acid and we'll get a different number that'll be lower than 7. And we'll calculate the pH of a base, which will be higher. But that's a problem for future you and me, because we're out of time for today. I do want to thank everybody for coming to the lecture. Make sure that you get quiz number 8 in tonight and quiz number 9 in tomorrow. Again, those do close the next day. I don't think you need me to tell you that. The dates that I put on here are the due dates and not the closing dates. But the big thing that we're going to have this week is exam number 2, which is on Friday the 11th. Make sure you're using that Discord. It's been kind of quiet. If you have questions to ask of either me or other students, make sure you get those out there, because there's not much time to study, right? We're almost done. In fact, blinking at the start, I told you blink and you'll miss it for this quarter, and it is zoomed by. I mean, from my perspective, at least. So hang in there. You're almost at the end. All right, get those quizzes in and study for the exam, and I'll see you tomorrow. Take care.